Today's learning goal is to use the kinematic equations to solve one-dimensional constant acceleration problems. Use the kinematic equations to solve one-dimensional constant acceleration problems. So we're going to introduce these three equations today. These are called the kinematic equations. They're appropriate to use when we have motion with constant acceleration. So for example, when we have free fall, or we have a car accelerating, or like hitting the brakes, anywhere where you have an object that's speeding up or slowing down at a constant rate. So let's go through them very quickly. The first kinematic equation on our list, and these are in no particular order, is one that we've already seen before. This is the acceleration equation. Acceleration is equal to a change in velocity over a change in time. Vf is v final, vi is v initial, delta t is our change in time, and a is our acceleration. The next equation on our list is a new one. This one is that the final position of an object is equal to the initial position of the object plus the initial velocity times the time, plus 1/2 the acceleration of the object times the time squared. And then the last of our three equations is also a new one. This one says that the velocity final squared minus the velocity initial squared of the object is equal to 2 times the acceleration times the displacement. Okay, so we should look at an example to see how to use these things. So let's take a look. We've got an example here. It says, an automobile starts from rest and accelerates at 3.5 meters per second squared after a traffic light turns green. How far will it have gone when it is traveling at 25 meters per second? Okay, so the most difficult thing of this, like any problem like this, is interpreting what the problem is, what the situation is that's being presented in the problem. So the best way to interpret this without too much difficulty is to go little segments of the problem at a time, right? So we'll just focus on a few words at a time, and we'll try to draw a picture as we read the problem. So it says an automobile starts at rest. Okay, so it means that here's the road. We have an automobile as a car. So we'll just draw a very simple car. Starts at rest, so this is very important. At rest means that the initial velocity of the car is 0 meters per second. Okay, and accelerates at 3.5 meters per second squared after a traffic light turns green. So this car is going to start moving, and it's going to be accelerating at a rate of 3.5 meters per second squared. So the acceleration is 3.5 meters per second squared. Then we want to know how far will it have gone when it is traveling at 25 meters per second. So some time later, the car will be over here. And it's no longer stopped, right? It's been accelerating, so now it's moving. And the final velocity of the car is 25 meters per second. And what are we being asked to find? It says, how far will it have gone when it is traveling at 25 meters per second? So how far will it have gone? This is a displacement. We want to know how far is the final position from the initial position. So this is what we're looking for, delta x equals question mark. Okay, so this should be how we start every problem, reading the question carefully and drawing a picture and identifying the given information and what we're looking for. So we want to try to understand what it is that we're being asked. And that's probably the most difficult step. Next, we need to think about which of the kinematic equations should we use. And one of the equations is usually the fastest way to get to the answer. If we pick the wrong equation at this step, we may have to backtrack and then select another equation. So it's important to try to be strategic here at this step to pick the correct equation that's the most appropriate for the problem. So notice we have initial velocity, final velocity, acceleration, and we're looking for a change in position. So the first two equations have time in them, and we have no time here in our given information. We're not looking for time. So that right off the bat tells us that probably these two equations are not the ones that we're looking for. Let's take a look at the third equation. Velocity final, okay, we have a velocity final. Velocity initial, we have velocity initial. Acceleration, we have acceleration. And change in position, that's what we're looking for. So the third equation on our list is going to be the most appropriate for this problem. V final squared minus V initial squared equals 2 times the acceleration times the displacement. So let's substitute in our values. The final velocity is 25. So 25 squared minus the initial velocity is 0. So 0 squared equals 2 times the acceleration, 3.5, times the displacement, delta x, which we don't know, so we're just going to leave it as delta x. Okay, so let's go ahead and start solving for delta x. 25 squared is 625. 0 squared is 0. 2 times 3.5 is 7. And these numbers are multiplying delta x, so 7 times delta x. And now we're trying to solve for delta x, so divide both sides of the equation by 7 to get delta x by itself on one side. We should plug these numbers into our calculator, and you'll find that the change in the position is 89 meters. Okay, and we're being asked how far will it have gone, so this is just the magnitude of the displacement. We don't need to specify direction here. They just want to know how far from the initial, so it's gone 89 meters. Okay, so now I'm going to give you a problem to try on your own. Okay, the problem says a skateboarder is moving at a constant speed of 1.75 meters per second when she starts up an incline that causes her to slow down with a constant acceleration of negative 0.20 meters per second squared. How much time passes from when she begins to slow down until she begins to move back down the incline? Okay, so take a moment to try this on your own, read the problem, and draw a picture, figure out which equation would be the most appropriate to solve this problem, and then solve. Pause the video now. Okay, so hopefully you've tried the problem because you need to try these on you really need to try these on your own in order to actually learn how to do them. So let's go ahead and draw a picture. So we've got a skateboarder moving at a constant speed of 1.75 meters per second. When she starts up an incline, so an incline is like a ramp. So here's our incline, and we've got a skateboarder down here at the bottom of the ramp. And she's moving with initial velocity, right at the beginning of the problem, she's moving at a speed of 1.75 meters per second. Then she starts up the incline, which causes her to slow down with a constant acceleration of negative 0.20 meters per second squared. So her acceleration as she goes up this ramp is a negative acceleration because she's slowing down. Right, her velocity is positive and the acceleration is negative, so she's slowing down. And then how much time passes from when she begins to slow down until she begins to move back down the hill. So we want to know when she gets to the very top of the ramp and then slows down until she stops moving for an instant and then starts speeding back down the hill. This is our ending point. This is where our final position is going to be when she's at the very top of the ramp and she's just starting to turn around to fall back down the hill. Okay, and so down here she's moving, but up at the top of the ramp, right as she just begins to turn around, right, her velocity has to go from positive to negative as she comes back down the ramp. So to go from positive to negative, we have to pass through 0. So her final velocity is going to be 0 meters per second. And this is an important thing to understand, that whenever you have a change in direction of the velocity going from positive velocities to negative velocities, it has to pass through 0. So here at the very top of the ramp, when she goes from moving in the positive direction to moving in the negative direction, the velocity is going to be 0. And then what we're looking for here is the time that passes between the initial and the final. So delta t is our question mark. Okay, so that's the most difficult step, I think, is reading the problem and trying to decipher what it's proposing, what's the situation here that we should be considering. And once we have all these different pieces of information written down in our notebook, it's much easier to continue. So now we need to decide which of the equations we should use. So take a moment to look. We're looking for an equation that has all these pieces of information that we can substitute in, and then we'll be left with the one piece that we're missing, which is the time. So the last equation does not have time in it, so this is probably not the correct one. So we're between the first equation and the second equation. Well, let's take a look. So acceleration, final velocity, initial velocity, change in time. So it looks like the first equation is the most appropriate for this problem. Let's take a look at the second equation very quickly. This one has position in it, and we don't have any position written down after analyzing the word problem. So the second equation is not going to be super helpful for us because there's position, and we're not looking for position, we don't know position. So this is not the appropriate equation to pick. The appropriate equation would be the first one. Okay, so we'll write that one down. Acceleration is equal to velocity final minus velocity initial divided by the change in the time. And our acceleration is negative 0.2. Our final velocity is 0. Our initial velocity is 1.75. And the change in time, we don't know, so we're just going to leave it as change in time. That's what we're looking for. So now it's just an algebra problem. We have to solve for change in time. So the first step we should do is multiply both sides of the equation by change in time to get change in time out of the denominator. And then, let's see, so we should divide both sides of the equation now by negative 0.20 to get delta t by itself. Right now it's being multiplied by this 0.2, negative 0.2. So we should divide both sides of the equation by negative 0.2 to get delta t by itself. So we're going to have negative 1.75 divided by negative 0.20. And then let's see what this comes out to. So put into your calculator these numbers. 8 seconds. Okay, great job.